I ain't playing, got a weird mind. If you work 8 hours, I'ma work 9. If the shoot tastes sour, you should taste mine. I'ma stay in power for a long time.
Okay.
Toss me the ball, I'm a really big hitter. Big picture, I'm a straight killer. Rising the song to the highest bidder. Got juice, got gas, I'ma move fast. New shoes, new tracks, like who's that?
So we're looking at the quasi-resonance flyback converter again. And I did some homework. Okay, this is a banger, but need to turn it down a bit. Okay. So, let's see. AC/DC flyback converter circuit. Let's see if I find a nice picture for it. Like a nice diagram. Yeah, this is a good one. So there's just a so I'll put this a bit down. And I will lock it. And basically, so here we have the AC input. So this we will have this bigger range done. Uh, 80 to 2, was it 265 or something? So here we have an AC signal, and then it goes through this rectifier. And we have a basically like a pulsed DC signal. And this is the current flow when it's closed. So when this is closed, it completes the circuit. And you have the current flow here going through the coil, through the switch, and the VDS, the drain to source voltage, is 0. And this is powering the load. So that's this one. Then when the MOSFET is open, the energy is transformed from the primary side to the secondary side, and it's forward biased here, this diode. And it goes through the load. And it also charges up this capacitor. And you can quickly see the most important calculations that you have to do. That is this input capacitor. It is the transformer itself. So Maybe I should do like this. 1, 2. This diode. I'm not sure if you have to do any calculations, but you have to select it at least. And probably also this C2. So 4. And I also know that you actually, yeah, there are more to this converter, but I'm not going to look at that now. Let's focus rather on the most important parts, the most important calculations, and I found some good resources to learn. Yeah, let me see if I can find it. So here's AC, here is then DC. But it's not like pure stable DC. It's like pulsed, so not alternating, but like pulsating. Okay, but no speculation here, no. Keep it simple. This is complex when you're doing it for the second time, or when you have not so much experience with something. It's good to try to stay locked in to one thing. Wait. Okay. Wait, just double check that the microphone is on. Everything is all right. Good, good, good. Okay. AC, DC, fly back converter design guide. I did find a good one from, was it Microchip? No, here. Yeah. From Rome Semiconductor. I think it was this one. Design procedure from AC-DC converter circuits. And it's all from, oh, maybe I start here. It's about firming up the specifications, like, selecting, I guess, for this specific design or this example. Then it's based off of that, selecting a power supply control IC. That would be the QR flyback converter, or I think in this case it was a PWM, or like a fixed frequency flyback converter, which has a bit lower efficiency then, because it's switching at a fixed frequency rather than using the valley switching, which gets you the lowest amount of switching losses, because you're switching on the MOSFET at close to 0 volt. Then design and peripheral component selection, prototyping, evaluation. I didn't go read into so much here. So this is an overview, and here is more a specific design. So this was the PWM AC-DC flyback converter. Here is a non-isolated buck converter. I didn't look into this one, but and this, I think, is a bit explanation on how you should go about it, and a bit just explaining what we're gonna do. First important task is firming up the required specifications. Normally, this is the first and most important task. However, since power supply specification cannot be determined until specifications for the entire circuit board are fixed, it is not uncommon that the task of establishing power supply specification is undertaken only. Yeah, okay. Maybe I read that as it can be a bit loosely defined, and unless it's specified by a customer that they want this type of efficiency, or they want, they know exactly what type of input. Maybe it's a bit, it can be loosely defined, which is good. It's liberating to think of it like that, because then you don't get, stuck in the details of designing or defining the start requirements or input requirements. Selecting a power supply control IC. So here are 4 different ones, I guess, or system transformer. Okay, so we are using a transformer here, switching. Right, let me see. Whether the AC-DC system to be employed is a transformer or switching type, a step up or a step down, or flyback or forward. And this is another thing where, you have this linear flyback forward. And they have their own, advantages and disadvantages. But let's not stop ourselves there. Design and peripheral components selection. Major transformation components like the transformers, bridges. I'm guessing the rectifier bridge, diodes, the output or the secondary side diode, input and output capacitors, and then components required for the IC, calculation and optimization of constants, and then the actual transformer design. So calculating reflected voltage. What else? Like number of windings to get the desired output. So I like this web page. At least it worked very well for me when I read through it. So size, inductance, number of turns, structural design, wire diameter, and layer construction. And I'm not sure how specific you have to, do all of this, but it's good to kind of have gone through it to understand, winding method, wire, the type of wire. I guess this is the size of the wire, how many turns. Yeah. Prototyping. Yeah. But we're gonna prototype, but we're gonna simulate as well, I think. Mass production. We don't have to go into all of this. Issues and considerations to take. Efficiency. Yeah. But then we have this one. Overview of design method of PWM AC-DC flyback converter. So this is also, it is a flyback converter. What actually means a flyback? When we say flyback, what do we mean? What does the flyback mean in the flyback converter? Refers to the period when the energy stored in the transformer's magnetic field during the switch-on phase flies back or is released to the load during the switch-off phase. This energy transfers occurs when the primary switch turns off, causing the stored magnetic energy to induce a voltage across the secondary winding, which then delivers powers to the output. Now that's basically what we wrote here, right? So that is, this part is the flyback. The energy stored in the primary side of the transformer is released, or it flies back to the secondary side and powers the circuit. And it's interesting of this design method that it lists up all the, selecting a power supply control IC. That's basically, the IC that will drive this MOSFET, whether it's external or internal. And then it will have some other, if there's a isolated one where it goes through a optocoupler here to give some type of input to the IC, to whatever it does. I don't know 100%, but that is cool. Okay, so we get that, the flyback. One of the most fundamental ones, I am sure. Maybe the quasi-resonance is a little bit more complicated compared to the fixed frequency, where I'm not sure what you have here then, if you can, yeah, I mean, we will look into that. Okay. So this is the isolated flyback converter basics. So a little bit explanation, then the design procedure, determining power supply specification, choosing an IC, starting off with transformer design, calculating numerical values, structural design, critical components, MOSFET related, C-in and a snubber circuit. So a snubber circuit with like a diode, resistor, and capacitor in order to because it's this leakage current. Something like this. That's the snubber circuit. At least what I've looked into, so I will learn more on how to implement that or add that to the circuit, but as you can see, it's reverse biased here. When the switch is on, or when the switch is closed, and when it's open, there's some leakage here, I guess. Yeah, I'm not sure, but there will be some current flowing here. No. But yeah. Yeah, here's the control IC to control the switch, rectifying diode, capacitor, and here you have the DC signal then to feedback path insulator element. And I really like this graph. So you have the inputs, clear or not clear, but probably a noisy input signal. It goes through the rectifier. Then it's goes through the capacitor, that will smooth it out to have these small ripples. And then this is low frequency, and it will be controlled by this IC here, and it will be a high frequency square wave. And then again rectified and gone through the output capacitor to smooth it out again. And then you have the step down voltage. It's pretty cool to see it. This is a very good image. So what are the characteristics of flyback converter? And we've already talked about this. The circuit chops the input voltage DC by using a switching transistor and transmits the energy to the secondary side via a switching transformer. The secondary side rectifies and smooths the output and converts it to a required DC voltage. Isolation by means of an optocoupler or tertiary winding. And here we can look more in the detail of the voltages and the relationship. So here's just a time when the switch is on and when it's off, and VP here's a reflected voltage, VOR, I think that's the reflected voltage, which is the ratio between the windings, so the primary side number of windings, and the secondary side times the forward voltage of the diode plus V out. So whatever you want V out to be, then you will know the reflected voltage. And I think you assume that value to be between, I read somewhere like 80 to 130 volts. So I think you assume this value, and then you are able to get the relationship, the ratio. So you will get a numeric value, and then you can see how, based off of how many primary windings you have, or secondary windings, you will see how many primary ones you will have to get the desired V out. Vs is a secondary voltage. Here's the drain to source voltage, where you see this oscillation here. Yeah, I need to learn more into this graph for sure. Okay. Some explanation between discontinuous mode and continuous mode operation. And in this particular design procedure is a discontinuous mode, apparently. So it's this one, where the current flowing through the primary side is based off when the MOSFET is closed, the current increases, and then time off, it transforms over to the secondary side. And then what is this? Presence of a zero current period between off and on prevents a continuous current flow. Yeah, so it's discontinuous current flow. Here it's continuous because which turns on and off at the same frequency as the switching frequency. Firming up the specifications, here we can, have it a bit loosely defined, like we had just 90 to 265. I think maybe we said 80. I'm reading a lot of articles, and it's sometimes I think it's at 80, sometimes 90, sometimes 95. But it doesn't really matter. It's for just to get going. Da, 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 And we would like to make one a flyback converter, but we want to make a quasi-resonance flyback converter. Texture power supply design. Design and selection of peripheral parts. Minimum specification to be fixed before starting the design phase. Input voltage range. Right, so here is US, Japan, output voltage, accuracy, don't have to worry about that. Output ripple voltage. A ripple refers to pulsation. Converted DC voltages contain pulsation that is related to the frequency of the input AC power supply, or the frequency of the switching conversion. Although naturally the conversion process includes smoothing filtering that does not reduce the pulsation to zero. There is a 400 millivolt peak-to-peak ripple centered on a 5-volt DC output. For example, the maximum value will be 5.2 volts with a minimum of 4.8 volts. This amounts to 5 volts plus minus 4%, barely satisfying the general accuracy requirement of plus minus 5%. Right. So you would have to be a little bit careful then, I guess. So setting the ripple to be low enough that it doesn't cause any problems with the operation of a microcontroller or something. Maybe. Insulation voltage tolerance. Some system specification require insulation for the AC-DC converter, industrial equipment, and the medical devices basically require insulation, and in some cases the identification of specific insulation level is provided. The electric non-conduction between the primary AC input and the secondary DC output sides. Okay. So basically the max a device is supposed to handle. Yeah, that's moving on. Well, operating temperature range. Yeah, it's nothing critical. We just know that this matters, right? Higher the temperature, lower the temperature, it will have an impact on how well something, in this case, the AC-DC converter is operating. It generates considerably amounts of heat. Critical problems may be generated. It's all good. We don't have to be too specific now. Oops. So, efficiency. 80% efficiency means 20% losses, which basically turn into heat. You need to have a good understanding of relationship between efficiency and heat. Okay. No load input power refers to the amount of input power that is consumed when no output current is flowing. That is the amount of self-consumed electrical power in the absence of a load. Which makes sense. You don't want to plug anything into the wall that is just gonna consume current when you're not actively using it. You're not charging your phone, but you have it connected. You don't want it to be drawing power, drawing current, leading to a higher electrical bill. Choosing an IC for design. So here's, but first we have a example power supply specifications. 85 to 264 input voltage, power supply system for wider input voltages, so it's more universal. And that's also what we want to build, is something universal that you can plug in, I guess, anywhere, right? Output, we want a 12 VDC, a DC output with a tolerance of 5% at 3 ampere. So with a 36 watt power rating. External out power transistors. Okay. Current mode type. Output ripple voltage 200 millivolt peak to peak. In order to satisfy this output here then, I guess. Voltage tolerance between primary and secondary isolation, 3 kilowatts AC. Optocoupler based feedback control. Guaranteed operating temperature range -40 to 85. Okay, minimum efficiency 80%, switching method. Maximum input power with no load, 0.1 watt. Low power type with a built-in start circuit. Okay, but then let's do our own efficiency. They used 80, let's do 85. Switching frequency, didn't say. Output ripple was 200. Let's do 300 volt. Millivolt peak to peak. And it's just, to select. Let's stick to only one DC then. With a 5% plus minus tolerance. Maximum input power with no load. Max power, no load. Let's also do 0.1 watt for fun. We have to then select a low power type with a built-in start circuit. And I think it was also temperature. Operating temperature 0 to 50 degrees Celsius. Where's the music? Yeah, something like that. Doesn't have to be perfect. So this is the example that they do, and then here they have selected a PWM controller IC, which I will put up here so we can have a look at it. We look at the data sheet. Or can maybe look here first. No, let's look here, it's easier. You can look at the features. So it's a PWM control type DC-DC converter. So it's switching on at fixed frequencies then. PWM type DC-DC converter, for AC/DC provides an optimum system for all products that include an electrical outlet. So as far as I understood, it's a simpler circuit to design compared to a quasi-resonance flyback converter. It's also a flyback converter, but it's the way it's controlled is different. So it has PWM current mode method, which you can look into what is frequency hopping function, burst operation frequency reduction function when load is light, built-in 650 volt start circuit, VCC pin under voltage protection, over voltage protection, CS pin open protection, leading edge blanking function, first cycle over current protection circuit, soft start secondary over current protection. Applications: AC adapters and household appliances, vacuum cleaners, humidifiers, air cleaners, air conditioners. Rice cooker. Basic specification. So operating power supply voltage range 8.9 volt to 26 volt. That would be VCC, which is here. And then VH here. Okay, I'm not sure how to operating current in normal mode. Oscillation frequency 65 for the P06 and the P10 100K. Here's the D max. I recognize it from the calculations that you need to do. I wonder if you use I don't know. Moving on. I/O equivalent circuit diagram. Charge function. Switching. B. AC monitor. Okay. Okay, now we looked into the IC a little bit. We don't have to do that too much. So basically, yeah, this is just one part of it. And as you can see, it's very similar to other types of converters. The quasi-resonance, maybe I will just search the block diagram or quasi-resonance flyback converter. See if we have an image. Well, it's so the difference between the fixed frequency and this is, I mean, here you see the chip and everything, but the leakage. So there's some leakage inductance here. So this just represents the inductance of the primary side coil. There's also some leak inductance and some loss capacitance. So the stray capacitance, or I don't know, just a capacitance here that. Oh, how was it now? I need to. But anyways, you are able to use this information because of the leak inductance, and then I think there's some, yeah, this driver is able to use that information to turn on the MOSFET at those valley. So I think this. Yeah, okay. So at the turn off of, or the time off of the MOSFET, yeah, the quasi-resonant, it takes that information, the leakage inductance and the CD, the capacitance at the drain node, and here is the inductance of the primary side and CD. I'm just jabbering on, but anyways, it gets this information of the valley point, so it's almost like a 0 voltage flyback converter, or where it turns on at the lowest voltage. So when the MOSFET is almost completely off, reducing the switching losses. But Google it, and you will also learn more. Okay. But yeah, that's this circuit. Effectively, it's all the same. It's just a different way of controlling it, different way of using that information. You can also search a QR flyback converter IC. 5th generation. And this is the one we have looked at before. And it's similar. It has the input rectifier. The in, which is used, goes through some protections, it says. The feedback also goes in here and also to the active burst mode. Ground, here's this input capacitor. And what is this then? Set D. Here's the bus number. The power MOSFET. So I think this maybe is zero crossing detection. Zero crossing detection. That could be the one that is determining this zero crossing detection. Zero crossing detection is a technique used to identify when a signal like voltage or current passes through zero, while valley switching, I was comparing the two just to understand if this is the information they take in order to determine that it's you know, at the lowest valley point. While a zero voltage crossing detector can be used to determine the valley for valley switching. Okay, and valley switching is the operation it enables. So yes, this zero crossing detector is then taking care of that. So that's how those two differs. This IC and the other. Here we don't have any. We don't take this and use it anywhere. It's just a starter, a clamp circuit. But yeah, this is the one we want to make. So let's just say that we will use this IC. So QR back converter IC. That's what it is. Our quasi-resonant controller. Controller IC. So I can do a much better block diagram in the future, at least. Zero voltage detection enables valley switching by turning on a power switch when the voltage across its terminals is at its minimum, or valley point, which minimizing switching losses and electromagnetic interference, EMI. This control method is sometimes called quasi-resonant switching and requires a zero-voltage detector to sense the resonant voltage, allowing the switch to activate at the optimal moment in the cycle. Interesting. So we can do up to 60 watt then with this output power of 5th generation quasi-resonant controller, 60 watt. And other than that, this current sense, the CS pin is connected to the shunt resistor for the primary current sensing externally and to the PWM signal generator block for switch off determination. Current sense. Oh, okay. Yeah, we don't have to go into all of the details or the features so much because I simply don't know what every one means. Fast startup achieved with cascade configuration. Okay, well, what cascode? Cascode. Built-in digital soft start. So I don't know the benefits of all of them, of course, but yeah, we don't have to go through in absolute detail. We know we're going to implement, or we're going to use this IC, this quasi-controller, quasi-resonant controller, normal operation. Um, yeah, maybe we'll be going back and forth, I guess, to this data sheet, but they have a comparison of quasi-resonant and fixed frequency flyback. Here we have the design guide for this one. Although this one was a little bit harder to follow. Um, and we're gonna make a spreadsheet for this. We're gonna make a spreadsheet. So based off our input, our input parameters, minimum AC, line frequency, everything that we set here, we can calculate this more easier and more. Oh. So here's a case study. First, we show a circuit diagram using the PWM controller IC for AC/DC. Here we see the input, filter, rectification, the AC monitor here. I guess clamping diodes. pH. Okay. The input capacitor, the bulk capacitor here. Connected between the, what do you call this? This rail to ground. Then you have a snubber circuit, a transformer. Here is this C11 capacitance here, the C. The external MOSFET here. I don't know what this thing is doing, but here you have the optocoupler current sense. So sensing the current, and I guess turns off the MOSFET if the current is too high or exceeds the extreme values. Here's the feedback through the optocoupler. Also a snubber circuit on this side, I guess, or just a filter. And this is of course the secondary side diode, and then the energy storage, the capacitors here that will supply the circuit when the switch is on. So now we're at the calculating or transformer design, calculating the numerical values. So this one is important. This one is essential. Setting a flyback voltage. So this is the design procedure. The listed items below describe the procedure for designing a transformer T1. The following procedure, T1 being this one then, or this whole thing here. The following procedure, you calculate numerical values and derive parameters for the transformer listed in the table below. For windings and symbols for the electrical current that flows, see the transformer schematic diagram provided in the lower right area below. Yeah, so here are the steps. The values derived as transformer T1 parameters. Core size, primary inductance, number of turns on the primary side, secondary side, and D. I'm not sure what that is, but maybe we can just not look at that so much. Setting a flyback voltage V or is equal to VO, the secondary V out plus the VF. Okay, we'll start writing it a bit down. Hold on, maybe I do like this. Reflective voltage is the same as flyback. This reflected voltage the same as the flyback voltage V or. Yes, it is. And here we have the calculation for that. So this is what we have done. The reflected voltage is equal to V out times the ratio of the turn or windings, number of turns of the windings of each coil. So the primary side and the secondary side. And then you can calculate you know the V in, and we know what we want on the V out, and we assume a value between, here it's 70, and a forward voltage of this diode is 1 volt. Yes, and how to set or how to assume reflected voltage. And this is I read about this, that based on this value, you put more strain on the MOSFET or on the diode. But that may be a bit too simple to say. How to assume reflective voltage in a flyback converter design. You can make an initial assumption for the reflected voltage based on your desired output and initial guess for the turn ratio. But that's what we set 100 because it should be between V or, it can also be V or, because it's between 80 volts to 110. Let's just go with 100. The forward voltage we said was 0.5. In this case it's 1 volt. But that's based on which diode you choose, right? So maybe we would have to go back and check then if the turn ratio is correct. Because here we get this ratio, and in this case it was the primary windings have eight more turns than the secondary side. So it's stepping down voltage. And then duty cycle is V or V duty cycle max is V or. Let's go with V or for now. Divided by V in min plus V or. And V in min is calculated like this. So let's add Another one. We're in min. It is the VAC min, right? The 85 VAC. VAC. Times 1.4 times 1.8. Okay. Maybe they could explain that a little bit though. But I've seen another circuit for that, or if not another equation. What is 1.4 and 0.8? You feel a bit stupid when you look at that and you don't understand, but how could I? How could I? So our duty cycle then is, so if this is so is this is 85 times 1.4 times 1.8, that's 95. Or just write here instead comment. Then we can calculate this. So here it's um, 100 divided by 95 plus 100. So 100 divided by 195, which is 0.513. Empirically, the desired duty max value is 0.5 or less if the calculation indicates a duty value greater. Okay. If the max is greater than 0.5, and adjust viewer. Okay. Why? terms of operating principles of the flyback converter, we choose a starting point setting of the flyback voltage in order to clearly identify the VDS of the switching transistor that is applied to the primary winding, that is the quantity V in plus V or. In another approach, it is possible to use the maximum duty ratio as a starting point. Okay. Calculating the secondary winding inductance LS and secondary side peak current. In succession, we calculate the secondary side winding inductance LS and also IS peak. To provide for margins such as an overload protection point, the maximum load current should be 1.2 times the I out. Okay. Okay, yeah. Where were I? Since specification for I out are 3 amp, IO max should be 3.6. So I out was 2 amps in our case. IO max should then be 2 times 1 point I out equal to no wait, I out max should be I out times 1.2, which 2 times 1.2, 2.4, 3.4 amps. That's I out max. Overload protection endpoint. Overload protection point. In terms of specification, Vout should be equal to 12 volt and the VF and duty values calculated in step 1 should be used. I think we didn't calculate VF forward voltage of selected diode. Assume first. And I think we wrote in 0.5 volts. V or VD. And then we can calculate, maybe I will put this up here. Wild max. Secondary inductance. I need to, clean up this so it's easier to see. Like if I can add like a formula or something. I don't think you can do that. Formula. So LS has to be greater than V out plus VF. VF times 1 minus the duty max D max D max. Oh my god, it's gonna be messy. Wait. Squared. So that's that's on the top. Divided by 2 times I divided by 2 times I out max times switching frequency max. And then the switching frequency. We didn't specify that. Switching frequency. And this is a bit interesting because they didn't specify that, I think. Maybe I'm wrong. But I think we had switching. No. No. We can look. So in their case, they used this one, which had 65 kilohertz. Yeah, so they set the maximum oscillation frequency type or 1A. Yeah, that's this one. So then we can look at R. Switch. Switching. Yeah, okay. I guess it doesn't really take a switching frequency then, no? And VAC min and P Out max. At least it's not fixed. To reduce the switching frequency difference between low line and high line minimum, zero crossing count determination is implemented. For the transformer design, the minimum switching frequency should be greater than or equal to 40 kHz. The maximum switching frequency should not be higher than 200 kHz in any line or load condition due to LEB. But did it say how much F kilohertz? Where's my so in this case it's switched at a fixed frequency, but what does that mean here? Hmm. Okay, but let's just there was a design guide here and they used 60. So define input parameters for 55. So let's do that. My middle disappeared. Ah, there it is. So 55 kilohertz. So F max. Or this is the maximum though, but the gate drive has been in a high state longer than the maximum on time. It will turn off to prevent the switching frequency from going too low. But the transformer design should not be higher than 200 kilohertz in any line. Okay. I will just try this. I'm not sure if this is correct. But then we're able to calculate this at least. ls v out was 12 plus the diode, so plus 0.5 times 1. Let's say it's 0.3 squared. And that's divided by 2 times I out max, 2.4 amps. I should do it like this. And then 200 kilohertz, which is calculator. So 1 minus 0.513 squared. 1 minus 0.513 squared times 12.5 so 2.965 divided by 2 times 2.4, 2 times 2.4 times 200, 960, 960. That's okay, wait. Okay, let's try and calculate this. So 1 minus 0.424 squared times 13 divided by and let's just write this down here. This is 31308. And then we have 2 times 3.6 times, oops, 2 times 3.6 ampere times 70 kilohertz. And then we take that is 504 4 3 1 3 0 8 8 divided by 4. Okay. Yeah, that is this 0.0085 or 8.6 microhenry. 8.6 microhenry. So what did I get here? 2965 divided by 60. 0.003. So we get then LS to be 0.0308 or 3 microhenry. Yeah. And then the secondary peak current, we have 2 times I out max divided by 1 minus 0.513, which is I plus peak. Okay, I need to go soon. But I'm very happy that I managed to go through these calculations. Or not all of them, but we're on our way here. IS peak is then 2 times I out max, which was 2.4 ampere divided by this relationship here. 1 minus 0.513, 0.487, which is 2 times 2.4 divided by 0.487. 9.85, but we can do another one here then. LP, so the primary side then. Primary inductance. LP is equal to LS times NP over NS squared, which is it's equal to LS 3 microhenry times 8 squared. Oh, not 8 squared. Square root. Oh, oh yes, squared. What am I? Okay, I made a mistake somewhere here then. I made a mistake here. I didn't use my calculator properly. Yes, I did. Yes, I did. No, I did. Yes, so 3 microhenry times 64. So LP is then 192 microhenry. Yep. Yeah, I can maybe 192 microhenry. Here 3 microhenry. 9.85 ampere. It's fun when you get into it. It was super overwhelming yesterday. So now we have, okay, we need to calculate also primary peak current, which is I primary peak, the secondary peak times NS, NS, and P. NS. Yeah, right. Okay, but maybe it was a typo or something first. But then this is 9.85 ampere times 1 over 8, which is I peak 1 divided by 8, 0.25 times 985. So 1.23125 ampere. So, or maybe just 1.23. Where the calculated LP represents one of the values that are derived as parameters for the transformer T1. The size of the transformer core is determined based upon the output power P out. The table below shows the relationship between general output power for a flyback converter and a required core size. Because the output power for this design is 36 watt, we select the EER28 core size. And since we do 24, we can do this one. So I think I also wrote up a core size EE25 EE25 transformer. So for example, this one, EE25, 15 to 30 watt. Primary reflected voltage, ambient temperature is less than or equal to 50 degrees Celsius. Ah. Cross section, core cross section. The primary winding turns MP must be set initially so that the magnetic flux density will fall within the tolerance range, since the maximum flux density BT for the commonly available ferrite cord is 0.4 T 100 degrees Celsius. By setting B sat to equal 0.35 T, and substituting into LP and IP peak, we obtain the primary winding turns NP. Yeah, because we just know the ratio, so we don't know how many turns or the winding count is on both the primary or secondary. So that's the next one, calculating primary winding turns and P. Yeah, let's stop there and I will continue again. Maybe tomorrow, we'll see if I continue with this design or maybe I do some work on the NFC reader design. But this has been really, really fun and very, yeah, I've learned a lot, so cool. But then thank you for watching. I hope you learned something too. Okay, I'm out.